Nice to see you all. Homework questions? Do they have them? Done?
Number 8 on 6-2. So this one, we are asked to find the area enclosed by the curves on the 0 to pi. So what were you having issues with?
Never mind, I thought it wasn't getting the bounds.
Oh.
And I was having trouble finding it. But I think it was just late at night.
Fair enough. Yeah, so this was like a problem we solved in class, if you needed to find the bounds. Of course, they would keep going, so you'd have to then default to the graph and not keep going. All right, well, never mind on that one. Any other homework questions?
I have a simple question on 6-1, question 5. The only question I had was, the second part is, one of the last parts is how much distance has it traveled, and you have to do like the absolute value of the function.
Mm-hmm.
But it had you split it up into the different integrals of that domain, like
Yeah.
the 2 to 5, because some of it's negative, some of it's positive.
Right.
But I was wondering if you absolutely have to split it up like that and then add. Does that make sense? You have to split up the integrals and then add, or can you just do one integral, the absolute value of that, and you get the same answer?
Well,
So
yeah,
can I get this-
how are you doing the absolute value, though? That's the issue. Like, how do you compute the absolute value of that integral without knowing where it's positive and negative?
So you do just one.
Yeah,
Yeah.
you do.
Okay.
Just like,
I'm
this
just wondering if
is,
there's like a short.
no, unfortunately not. And anytime you work with absolute value, you never really work with the absolute value directly, right? You always think, all right, well, where is this thing positive, and I just work with the thing on the inside, and where is it negative, and I work with the opposite of the thing on the inside. So it's never really like the absolute value, it's just there, you
Yeah.
know? So unfortunately, yeah, it's tedious.
Okay. That was it.
All right. Yeah, distance traveled for problems like this, I don't think it's difficult in the concept, but it's difficult in the sense that it's, what is there? There's 3 different integrals maybe you have to compute.
Yeah.
All the same antiderivative, but you've got like 3 different values, so it's just a pain. Did you have a question?
I think I had a question. It was last night's homework. It was, yes, 6.4 was the last problem, question 10. I thought this was a really cool problem. I saw 2 potential ways to do it.
Mm-hmm.
So, let me see. So we're probably around y, so it's going to be y. Yeah, so the way I did it is I did it with respect to y, and I integrated it from 1 to 3, I believe. I'm trying to picture the problem in my head.
Yeah, 1 to 6.
Might have been 6, but anyway, so the lower element of the lower bound of integration was 1.
Mhm.
I thought there'd be a way to potentially do it with 0, but you'd have to subtract the line for y or x equals 1. Would that work too? I don't know if that makes sense. You'd change the limits of integration, but you'd also change the formula you're integrating, and I was wondering if that would give us the same answer.
I guess I would have to see it.
Okay.
Do you remember it? Like,
Not off the top of my head is the problem, but I
Okay.
saw 2 potential ways to solve this one. I was just curious if they would give the same answer.
Yeah, I mean, if you're messing with the bounds, then it's gonna mess the function up. So
Yes.
I
But then the way you would
that-
change the function, I was just wondering if that would give you the same answer. I didn't have time to check it out, but
Yeah.
it just seemed interesting.
I would say that probably.
Okay.
But I would have to see what we did for sure.
Okay.
Yeah, and I don't know if we actually did. Where did we go? 6.4 is totally gone. I don't know that we did that question yet. I don't think we did. Just check. I don't think that.
What was the one you said we'd come back to today?
I think it was
PDCC.
similar to that problem.
Okay.
I believe. I don't. What was that? Yeah, this one.
Okay.
So it's kind of similar. The one in your homework is a right circular cone, so it's a little bit more difficult because you got to find the equation of the line for the function. But it's based off the same idea here. So like if you want to just show me here,
Okay.
I'm happy to look at that. Yeah. So any other homework questions? So yeah, I guess we can revisit this. We did, the last example in 6.4 that we looked at was where we were revolving it around a different axis, not the x or not the y axis. And then we did have another example like that, but sort of running a little behind. So here it says use the shell method to find the volume of a solid formed when a hole of radius 2 is drilled symmetrically along the axis of a right circular cylinder, height 6, radius 4. Okay, so let's do this. Just kind of drawing out what we're dealing with. Height 6, radius 4. So we're trying to find the volume of something like that. But again, when we're given like a figure that's complicated but symmetric, we don't really want to think of in terms of the volume, right? We want to think about summing up a bunch of areas times a little tiny thickness, which would give us the volume. So we're gonna sort of translate this into a simpler situation and think, well, what if I revolved something around this axis? What would I have to revolve around this axis to get this shape? Huh? A line, yeah, basically a line, right? But what we want the thing to do is actually generate something that has an actual radius this time. Whereas like if you take a line and you revolve it parallel, you know, we don't really have a thickness here, right? It's just a line, no thickness. So we actually want to give that some dimension because we do actually have this thing here. So I guess we should also draw that. We've got a hole in this thing here, so whatever that looks like. And we have this hole here. It's kind of like this hollow cylinder here. Okay. Of radius 2. So if this is a radius 2, that would put us over here at 2. And you know, I would center it. You don't have to center it, but then you can utilize symmetry.
Okay. The height is 6, so we'll just mark 6 up somewhere up here, and a radius of 4. So where does this thing go out to? Like if we're gonna put this cylinder, quote unquote, on in the first quadrant, where would it go out to? Like right, this would be the radius of the cylinder. It's 4. So we're gonna mark 4 as well. But we don't care about this space here because that's, this space right here is the hole. So our cylinder, I'm just going to cheat and draw this here. Gonna have this thing here.
We have a rectangle. If we rotate that rectangle around the y-axis, can you see it in your head that it would give us a cylinder with a hole in the middle?
Okay, so we've accounted for the hole by just kind of spacing out from the axis of revolution. We've got our radius that ends the cylinder or the rectangle at 4 and its height of 6. So all we want to do is just rotate this around the y-axis. So we're gonna slice or fill this rectangle up with rectangles. Not really necessary. Just again to get sort of our bearings, we're integrating with respect to x. Or if we're using in the shell method, we're gonna slice parallel to the axis of revolution. So there's our slice integrating with respect to x. And then the shell method, I don't guess it says shell, but we're going to use shell method. 2 pi RH, we've got to identify the radius of each one of our slices and the height of each one of our slices. So the radius would be what? The radius of our cross section that we're looking at now.
It'd just be X.
Just be x, right?
X.
Remember, the radius is always in the shell situation. It's always the distance from your cross section to the axis of revolution. So more generally speaking, our radius is running in this direction. It's the right minus the left. This is some x value, and this is 0. So our radius, we'll just write it out like this. Radius is x minus 0, right minus left. And the height?
6.
6. Yeah, it's always, the height of all of these rectangles are always 6. So then we're just going to integrate that area, the cross-sectional area, 2 pi RH. So we're going to say the volume is 2 pi R times H. The bounds are where? From where to where?
2 to 4.
2 to 4, do y'all agree? Bounds are from 2 to 4. All right, that's it. That's your setup. That calculation will give you the volume. Any questions on that? Okay. So what is this? 72 pi. So kind of like similar thinking for the one involved in your homework, but the one in your homework is a right circular cone. So it's, like this thing. Again, I would just center it at 0. But in an instance like this, we would, our cross sections are running like that. It's not as straightforward with the cylinder. Our cross sections, the height, they never varied. It was always 6. But these cross sectional heights vary, which mean that your heights of those shells are going to be determined by that function. So then based off of the information they give you, you've got to find this linear function right here. So that's kind of the only difference. Make sense?
So would R be again x minus 0?
Yeah, right. As long as you're revolving it around the y-axis.
It'll always be, okay.
Yeah. So it's that distance, x minus 0. Okay. Any other questions here? So let's go back to this one. I know we wrote down the answer. Just curious, did anybody do that? Okay. Why don't we take 5 minutes to set this up? Does anyone want to share what they have for the setup? Just the setup, not like evaluating it.
Too high
Volume is too high.
from 0 to 1. 0 to 1 square root of y.
Square root of y?
Yes.
Okay.
By 2 minus 1 dy. Yep.
Do y'all agree? Does yours look different?
If we're doing the this, it's just pi. It's not particular.
Right, yeah, so this says disc washer method. So what if we were doing the shells? Did anybody do that in addition? So maybe did you get that?
Says, use the shell method.
Yeah.
Our paper says shell.
Shell method, yeah.
Oh, it does, okay. How curious. So is that what you got? That looks like shell method if we're revolving it around y equals to 2. The shells are parallel, so that's dy. So that looks like a shell method to me, not disc washer. It's the same region we had in the previous problem. That was 1, the square root of x. I'm sorry, x squared. We're revolving around y equals 2. Let's just say that's up here. Y equals to 2. Shells then are parallel to this. Okay, so there's one shell. Remember, that's the height of the shell. This dimension here is the height. This dimension is the radius. At some y value, we have to measure that distance, top minus bottom, 2 minus y. So that's your radius. Everybody agree? So what's missing? Okay, 2 pi times r times h, is that the height of the shell?
Oh, 1 minus
1 minus, right? If this is the height, how do we measure that?
right to left.
Yeah, from right to left. Right minus left. That's the height of the shell. Right minus the left. The right function is always 1. The left function needs to be in terms of y or solve for x and not y, right? So that's square root of y as the left function. The right function is 1. So this should be 1 minus the square root of y for the height. Any questions? So draw these things out. Even if it's the same region over and over again and you're doing different methods or rotating it around different axes, just draw it out again. I think that's typically when I see people miss these problems on the exam, is they've literally drawn just one thing out and they're trying to fit all of these other situations into that single drawing. And you have a hard time orienting and saying, all right, well, if it's this, it's dy. If it's this, it's dx. That's typically the biggest problem on the exam that I see. It's not that people are using the incorrect method. It's that they're integrating with respect to the wrong variable, which I guess entails that you were using the incorrect method. So it's super, super important
Anyone have any questions? Yeah.
So when I was first trying to do this, I got confused with h, where I was trying to find y minus the square, 1 minus the square root of y. Could you explain how to get that? I figured it out over time, but. just in
Okay,
case, yeah.
the height, h?
Yeah.
So like when you first were doing this, what did you go to as the height?
I just assumed it was the square root of y, and I wasn't taking into account that we had that x equals 1.
Okay.
So I was doing that right minus left for it.
Okay.
But I was looking for another y, but I never seen one, so I just kept confusing myself because.
Yeah. Yeah, did you happen to draw this out at all?
Yeah, I did.
Okay. Yeah, so the advice that I have is to, if you have to measure that distance, then you just have to take the right boundary minus the left boundary, even if it's a vertical line. I don't know. I don't know how else to say it.
Yeah.
Because
no,
you are
it's just-
measuring that distance.
Yeah,
Yeah.
that's what I forgot to do, so.
Right.
And I guess like what helped me is like if I tried to do left minus right, then I get a negative,
Volume.
yeah, volume. I mean,
Mhm.
that's impossible. So, or you get a negative distance to begin with. And so
Yeah.
I tried that.
Okay.
Then
yeah.
I was like right minus left. Cool.
Good point. Good point. Yeah. Yeah. If you did left minus right, then your volume's going to be negative. Yeah. Any other questions or comments on that? Okie dokie. So that one we just expand out, right? We expand this out, and then end up integrating powers of y. Plus, we have okay, so we just expand out powers of y. It's sort of tedious because you've got these fractional powers. Lower boundary of 0 makes it pretty easy. Upper boundary of 1 makes it a little bit easy too. So anyway, 17 pi over 15 is what you should get out of that. All right.
With this, you're gonna do the top minus the bottom. But I get confused because it's around like
To 2.
it's still just, it makes sense to top minus bottom, even though it's around.
Well, like it depends on what you're measuring, I guess. If you remember with the disk method, you have 2 different radii. So let's try to. Whatever. I'll just draw it again. So this. So first of all, if we're gonna revolve around the line y equals 2 using the disk method, which way do our cross sections run? Yeah, up and down. Parallel, or sorry, perpendicular for disks. Disks are perpendicular to the axis of revolution. So then we would have to integrate all of this with respect to x. I probably can't draw this very well, but the thing is with the disk method, let me draw this here. This. Oh, that's not good. Let me try that again. So with the disk method, you're kind of getting this. I don't know if that's helpful, but you're sort of getting this solid here, and there's nothing in the middle. When we look at this cross section here,
revolved about this axis. It's not actually a disk that we're getting, because inside there is completely blank. There's nothing in there. What we want to measure is this right here. This outer part. I don't know if that's clear or not. So in that instance, we have two different radius, right? The disk method. It's really the washer method. So it's this thing. What is the larger radius here? Yeah. So this distance from here to here, right? Because that's the outer boundary of that figure once we revolve it around this axis. The inner radius would be what?
X squared.
Yeah, the distance from here to here. So once we've sort of established that, now we're looking at the top minus bottom for each one of those. The top for the outer radius is 2, the bottom is 0, right? So you see the outer radius doesn't change. The outer radius is always 2 here. It's the inner radius that changes. So we have, in blue, we have the outer radius squared, so there's pi capital R squared minus that purple. Again, this radius, what is that radius? Lowercase r.
This would be like x squared minus, x squared minus 2.
Close.
No, the 2 minus x squared.
Yeah, there you go. Top minus bottom, 2 minus the function 2 minus x squared. Right, that's lowercase r, and then we have to square that. Lowercase r squared. And then that's the setup for the washer method. dx. And of course, x also ranges from 0 to 1. So volume's volume, but if it, you just gotta be really specific, right? If the test says, hey, use this method, it says use the dishwasher method to do this, and then you're giving me this right here, there's really no redemption. Like I can't give you any points because you use a totally different thing. It's like totally wrong. So you gotta be super careful. That's why a lot of people lose points on the first exam too, because like I can't really give you partial credit for something like that if it's just totally the wrong thing, right? It's like me saying, hey, add 2 plus 2, and you say, oh, let me multiply, and then divide or something. I don't know. But this, washer method versus shell method there. Anybody have any questions? Did that help, Allison? All right, then we'll end 6.4 there. We'll start 6.5. So in 6.5, remember chapter 6 was all about what can you do with integrals? So we've seen displacement, distance traveled, we've seen areas between regions, we've seen volumes. Now we're going to look at arc length. And what we'll see towards the end of this class is another way to define curves. Right now we just know sort of this explicitly defined, here's some function of x. But we can also look at them like parametrically defined, where we let x and y be determined by a single parameter. And those can look really crazy. There's all kinds of things here. Instead of trying to draw it by hand. Refresh that so it's my background.
can measure something parametrically or in polar coordinates and also compute the arc length. So we will look at both methods. It's just the parametric stuff doesn't come until the last unit. But it's worth mentioning at this point. We can, as you would expect, compute the arc length of something like that. We'll just put that in for our parametric. We're here in 6.5, we're looking at the explicit way to compute arc length. So there's just traditional functions. Okay. I guess we'll derive this the best we can without like too formal of a proof. So sine from 0 to pi. And so we're going to use that to sort of justify where the formula comes from. But let's say we want to measure the length of that curve. What we're going to do is, it's sort of that slice and sum approach once again. So instead of trying to measure the length of the curve, what we're going to do is just break this up into line segments. So maybe like this line segment, and so forth. And of course, that would give us a pretty crummy arc length for that figure. But what we're going to do is we're just going to make those line segments smaller and smaller with a limit, with the sum, and we have to add all of that up. So that's where integral comes in, making the number of line segments we're putting in that curve infinite, and then summing all of that up. So an infinite sum is an integral, right? So, just keeping that in mind, we'll focus on just one, because all we really need to do is figure out how do we compute that red length, and then we're going to add all of that up. Okay, so we'll just call this, and I'm not going to be like super technical with the notation, so we'll just call that one L. And we'll have our right triangle here. But as a general sense, if you wanted to think of this generally, what we're going to have is just infinitely many of these kinds of things. Since this L is actually, in the kth subsection or kth partition, it's more technical if we refer to it as L sub k, because we're going to let k go to infinity. But I'll try to avoid using that. This distance here, notice it's just a distance in the x direction, right? So all of that's going to vary. We're just going to simply label that as delta x first. It's a change in the x values. Same thing with the y. We're going to label that delta y, because it's just the change in a y value. So that's what we're going to work with just to derive the formula. So here's a little bit better of a representation. They're using 6 line segments for that. We're taking this thing here. Trying to figure out what L is, so we'll use the Pythagorean theorem and solve for L. That's what L is. But it really doesn't help us, like if we're thinking like, hey, I've got to use an infinite sum on this, it's not helpful. Like this change in x is because it's a function of x, more or less. But the change in y is useless. What does that change of y look like in terms of x? We're going to manipulate this a little bit and then talk about something from Calc 1 just to justify this formula once again.
we're going to factor out, excuse me, delta x squared under the radical. And so we'll have our 1 plus delta y squared over delta x squared under the radical. And really doing that, the reason for doing that is twofold. One, we can now take the square root of delta x squared. So we're just going to take delta x. And two, it gives us a means to work with this thing now, because delta y over delta x squared, we're going to look at it as the quantity squared. So does when we compute delta y over delta x, does that sound familiar, like something we've done before? What is delta y over delta x?
dy dx the derivative.
Yeah, it's the derivative. We'll see why it's the derivative squared, right? In particular, though, a change in y over a change in x gives us a slope, which is our derivative is slope. Yeah. So let me. I don't know if I don't have that. But the theorem from Calc 1 that allows us to manipulate delta y over delta x is the mean value theorem. So you don't. I don't think it's crucial that you remember the mean value theorem. I'm not going to test you over it. Let me see if I can find it. Very quickly. So the mean value theorem says that if you've got some function that's continuous on a closed interval, differentiable on an open interval, what does differentiable mean again?
Continuous?
What?
Continuous?
Yeah, if it's differentiable, well, if it's continuous at a point, doesn't mean it's differentiable. So differentiability implies continuity. So it does mean continuous. But more broadly speaking, what does it mean?
It in general has to be like a function of x that doesn't have intervals or anything.
Okay, so yeah, right, no holes, anything like that. That's still building off the idea of continuity, of continuousness. When I say this function's differentiable, how about this? The function 1 over x is not differentiable on the interval from 0 to 1. What does differentiable mean?
It means you can find the slope.
Right, it means you can find this, you define the slope. It means that you can compute the derivative in that interval, right? So the function's continuous on the closed interval. The derivative exists. You can compute a derivative is what differentiable means. So then there's at least one point in this interval. This AB is on the x-axis. So there's at least one x value that we're going to call C, such that f of b minus f of a over b minus a. What is f of b minus f of a over b minus a?
Slope.
It's just slope, right? This is that's what that is. So there's if the function's continuous and differentiable, then there's a location in that specific interval where the slope, specifically the slope of the secant line, is equal to the slope of the tangent line. So why does that matter for us? Get rid of this. We'll look at a picture of this too, just solidify. So for instance, here's, I think we have this in our notes, but the green line is the slope of the secant line. That's f of b minus f of a over b minus a. And what we're saying is there's some location C in between a and b where the slope of this green line is the slope of this line here. In other words, the slope of the tangent line, sorry, the tangent line and the secant line are parallel. Their slopes are the same. And so wherever that point happens, here it's at this point, you know, for other segments of that curve, it could have been here, could have been here, right? It's just somewhere in between that A and that B. So that allows us to not work with a change in Y over a change in X, but it allows us to work with the derivative as opposed to, I guess they're both slopes, but it allows us to work with the derivative instead of the secant line. So just for reference, we'll put this in here. With this picture. So from the mean value theorem, we get something like this. And not only do we get something like this in that particular segment, we get something like that for each line segment we're approximating that curve, the length of the curve with. Okay. So then we copy this. Oops. Make sure that's still there. So then, based off of the mean value theorem then, remember this length was just a generic length for a line segment. But with this theorem, what we're able to do is to turn this into the derivative. Okay, so we have delta x times the square root of 1 plus f prime of x squared. Yeah, being a little less technical with the notation, but we're just going to take all of these sub k's and then add them up. Okay, so then is everybody okay with that? Slope turns into the derivative. We have a delta x times the square root of 1 plus f prime squared. And so when we let those go to infinity, somewhere we get our integral for arc length. I think they call it capital L. So the square root of 1 plus f prime squared dx. And of course the bounds depend on, you know, I want the length of this curve from 3 to 4 or from 10 to 15, right? But that's how we measure the length of a curve. Yeah, it's on the next page. So f has a continuous first derivative on the closed interval. Then there's the formula for the arc length from A to B. So what we see here, the arc length and the next section, surface area, you also see a similar kind of formula. But we are taking the antiderivative with derivative. So, you know, you have both operations going on. There is a tendency to, I took the antiderivative when I should have taken the derivative. So, you know, make sure you're like keeping those things totally separate. So example 1 just says set this up. So it's the length of the arc that we looked at first, sine x from 0 to pi. I don't know, you do it however you want, but typically I would at least find kind of separately what 1 plus f prime is, or sorry, 1 plus f prime squared is. So I usually just start off by finding the derivative of sine is cosine And then we have to square the derivative. And then we have to add 1. Okay, so all of that stuff you end up with there has to go under the radical. So the arc length is the integral of the square root of cosine squared plus 1 dx. And the bounds are given to us from 0 to pi. Okay, so that's the basic idea. You've got to find the derivative, you've got to square it, you've got to add 1 to it, and then you got to put all that stuff under the square root. So as you would expect, most of these things were sort of limited because even like computing the integral for the square root of cosine squared plus 1, that's a really difficult thing to do. We don't have techniques to do that yet. So the ones that we see here, until we learn other techniques, one of two things happens. One thing, the radical, the square root just goes away because the quantity you have under here is a perfect square. If the radical doesn't go away, then it's a u substitution that you can use to solve it. Okay, so like for instance, find the arc length of 2/3 x to the 3/2 from 3 and 8, from 3 to 8 rather. Okay, so we're going to find the derivative first. What's the derivative here?
X to the 1/2.
X to the 1/2. What do y'all think? X to the 1/2? So derivative, we've got to move the power down, multiply, and then subtract 1 from the power. 2/3 times 3/2 times x to the 3/2 minus 1, or 2/2. Okay, and then we square it. So there's our derivative squared. And we have to add 1. So I don't know, it doesn't really matter when you do all this, you just have to do all of it. So that x plus 1, that is our derivative squared plus 1. So that's going under the radical in this arc length. So there aren't any squares, doesn't go away, so maybe you can just do that without u substitution, but I think most of us would see this is a u substitution. What are we going to let u be?
X plus 1.
Yeah, x plus 1. That way, du is just dx. So we're just integrating u to the 1/2. With respect to u. So feel free to find the antiderivative, resubstitute for x if you want to use the bounds from 3 to 8. If you just want to stick with your substitution, then we have to use the bounds 4 to 9. Because u is x plus 1, right? And these bounds are for x. That's x and that's x. Come over here. Just a power rule again. 3/2, we have u to the 3/2 times 2/3. Evaluated from 4 to 9. This 2/3, plugging in 9, we've got 9 to the 3/2 minus 4 to the 3/2. So it's going to be some decimal. Or is it? So we've got 2/3. 9 to the 3/2 would be what? 27, right? 27 minus 4 to the 3/2 would be 8. Okay, so we've got our exact answer, but the next one we'll look at, you kind of get the idea of both situations you encounter. None of these are going to be like, if you end up with a function that you can't use substitute, or it's not a perfect square here with arc length, then you've done something wrong. Because all of these problems in this section are set up so that you can integrate them easily. So if you get to something that you can't use substitute, or the square roots and squares don't cancel out, you probably need to go back and check your work. When we look at this kind of thing, similar in 6.6, it's a little bit different. But again, we are limited in what we can do with integrals. So even the ones in 6.6 are set up so that things kind of algebraically cancel out nicely. I think we'll take a break and then we'll look at more examples. A little bit more complicated, or involved rather. We can also find the arc length with respect to y. Just view what we just did and rotate it 90 degrees. It's the same idea. So here we have, find the arc length of the function x for y between 1 and 2. So the first thing we want to do is find the derivative of the supplied function, x prime. So x prime would be what? I'll do this one. Derivative of y to the 4th over 4 is y cubed. So remember with these things, you might do a quotient rule here, but I think it's easier to think of this as 1 over 8 times y to the negative 2. I mean, quotient rule works as well, but. So if we've got our negative 2 coming out front to multiply that. Subtract 1 from the power. So there's the derivative. We then square the derivative. Just write it out like this first. So squaring, we get y to the 6th. Last term squared, we've got a positive 1/16 y to the negative 6. And then 2 times this product, the y's go away, it's y to the 0. 2 times negative 1/4, negative 1/2. So just like keep this in mind when we square the difference of two things. That's a squared minus 2 times a times b plus b squared. Okay, so there's our derivative squared. Then we need to add 1. So when we add 1 to this, we just get y to the 6th plus a half plus 1/16 y to the negative 6. So the derivative squared plus 1, we have to put that under the radical. Do we want to put it under the radical like this? Is there another way we can write this final product?
Yeah, it'd be the top expression just plus 1/4.
Right, yeah, it's the same thing we started with before we squared our derivative. It's just there's an addition in between instead of subtraction. Right. So just note the difference between a plus b squared and a minus b squared. It's only in that middle term. The last two terms, a squared and b squared, are exactly the same. So that's the same as that, and that's the same as that. Nothing changed there. What's different? The only thing that's different is the middle term. The middle terms are just opposite of one another. So we've got a negative 1/2, that was this thing minus this thing squared. We turn that into now a positive 1/2. So we're going to just work this backwards. Here's our positive 1/2. All of that stuff is going to be condensed. As a quantity squared. Does that make sense? Otherwise, if you leave it like that, you're not going to be able to integrate it. So it's y cubed plus 1/4 y to the negative 3rd is how that derivative squared plus 1 simplifies. So let's just write this out. Arc length is the integral, the square root of our derivative squared plus 1. So that makes things a whole lot easier for us to compute. And we're from y values from 1 to 2. Because all of that stuff, the square root and the square, of course, cancel out. And then we're just integrating powers of y. Does anyone have any questions? Okay, that's 123 over 32. So just keep in mind that pattern that we wrote out, a minus b squared, difference between that and a plus b squared. I think it's like really important because it happens a lot in these problems, right? The square root typically goes away with some of these more involved functions. Okay. Any questions? All All right, so I want y'all to try the arc length of 1/2 e to the x plus e to the negative x. So this
That's what it is.
So that's really just -1/2, right?
But that's okay.
Yeah. So yeah, when you add one to that. So if you've gotten that far, the answer should be 3/2. Curious. I'll give y'all a couple more minutes.
Okay,
Yeah.
thank you.
You're welcome.
So I didn't write that. Oh.
But you already had one, so and then you plug that back into the expression, and then you can see it's considered the square function. Hold up, yeah. Yeah.
Okay. I was trying to do it in my head, and I was like,
Does that kind of, that makes sense?
yeah, as long as you can sort of going back to it.
Like, yeah, putting it back into the.
I would write that out soon.
The square root of 60 squared is 7 works, and the expression. It's just, once you add 1, 2, minus 1/2.
So I just wrote it down here and then I had
Instead of being plus
Since this difference, this one was your innocence square, and this one was your innocence square. Right, because they only differ like 2. It's the same number, but they're opposite side. And so that always
So the square term here, the cross term rather, the 1/2 e to the x times e to the negative x, you want to simplify that fully. That's just going to be e to the 0, which is 1. So write it as negative 1/2. That way when you add 1, you have a clear like term to combine it with. I would recommend like writing all of it out fully, because again, if we're basing this off of these two formulas, the a plus b quantity squared and the a minus b quantity squared, you know, one of these a plus b or a minus b is going to be your derivative, and then when you see them expressed like completely out, then it makes it very, very easy to determine if when you add one, it's actually going to give you the other squared, the a minus b or the a plus b. Because again, the only difference is here. These two numbers are exactly the same. They're just opposite in sign. So you have this expanded thing out. Before you put it into the radical, you just want to rewrite it as the left-hand side before you take the square root. If it doesn't work out that way, then you're stuck with most functions because we don't have other techniques. So again, we've got to kind of, you know, work with the fact that we're limited in what we can integrate, so these things should work out nicely. And if it comes out to be something funky where you're like, oh, I don't know how to take the square root of that, either you forgot to write it as a quantity squared, or some of your algebra is wrong. So at that point, that should be your prompt to go back and look over your work. So I just wrote all of this out, and when we add 1. We get that, and I know this was already, I know this thing factored. You know, this was my a minus b, if you will, squared. I saw that directly from the derivative. So again, just difference in sign here. This is now a quantity a plus b squared. So our derivative squared plus 1 is actually 1/2 e to the x plus 1/2 e to the negative x squared. And we take it a step further, we have to take the square root of that, so bypassing that step here, arc length, we go from negative ln2 to ln2. I'll just write it out. Does anyone have any questions? So then the antiderivative we get 1/2 e to the x minus 1/2 e to the negative x. There to there. So it's like this is one of those u substitutions that you should hopefully remember without u substitution, because it's just much more efficient.
whenever you have like functions like this in linear arguments, you know, if you think about taking the derivative, using the chain rule, you would say, okay, we'll multiply by the derivative of the argument, or multiplied by the derivative of the power when we're taking a derivative. But the antiderivative is just the reverse of that. So instead of multiplying by the derivative of the power when these arguments are linear, you divide by that result. That's why when you integrate like sine of 2x, you end up dividing by 2 instead of multiplying by 2, because it's an antiderivative, not a derivative. But if not, your u is negative x. So ln2, and I'm just going to take the 1/2 out. So you take the 1/2 out, we have e to the ln2 minus e to the negative ln2. There's f of b, if you will, minus f of a is e to the negative ln2 minus e to the ln2. So you should know these exactly without calculators, but remember the negative, before you cancel, the negative goes up to the top of the power of 2. 2 to the negative 1 is 1/2. So e to the ln of 1/2. 1/2. So we have 2 minus 1/2 minus 1/2 minus 2 gives us 3 times the 1/2 out front gives us 3 times. Do y'all have any questions? Okay, and then just a summary of both of those there. And that'll end 6-5 if there aren't any questions. All right, then we'll start 6-6. So 6-6, we're looking at the surface area of a solid that's generated by revolving around an axis again. The derivation in your textbook is based off of this notion. It's kind of the same idea. What's the area of each little segment here? So we're going to look at this segment here. When that thing gets revolved around the axis, we create this figure called the frustum of a cone. So it's just like, you know, a right circular cone with its top cut off. So their derivation is based off of slicing and summing a bunch of these things. It's rather involved. If you want to look through it, if you want to look through anything we do in class where you don't feel like we justified it enough, feel free to look at the book. Not everything here that we do is actually proved in the book. There are some things that they say this is beyond the class to prove. But if you ever feel like we're not like covering something in depth enough, you can always go back to the textbook if you need to. And I just want you to think about where the formula comes from in a different way, but so like if we just looked at the area of this thing, and that area is just a linear dimension times a linear dimension. So if we just take this circle, it's this circle, it's this circle, right? If we just take that linear dimension, which is just the circumference of the circle, and then we multiply it by this linear dimension here, and we have the area. 2 pi r times h is the area. So think about that same way when we have a function like this.
we're trying to find the surface area of something like that. This is our function, f of x. And so cross sections here, if I make a slice into this, what am I actually looking at? If I slice into that solid. Circle, right? It's not as simple as 2 pi r, because we see the radius of that circle, varies as we go along that function, right? But we have linear dimension. What's the other linear dimension we're going to multiply that by to get the area? The height. How do we measure the height of that thing? Because it's not straight.
The arc length.
The arc length, exactly, yeah. So we have this linear dimension times that linear dimension. We'll just say height is equal to arc length. Okay. 2 pi r. Of course, we know r is what? R is actually defined as, what's the radius of this particular circle I drew? Half of, yeah, the x, or top minus bottom. It's this length again, top minus bottom. That's just f of x minus 0. So that's the formula for the surface area. We have to sum up all of those, 2 pi times f of x times the arc length, which is the formula we just saw in the last section. So here you go, the rest of the derivation and the definition or the formula for surface area. You've got 2 pi times f of x, that's your r, and then here's your arc length. All right, we'll come back and make a little note on this. It's a very similar process to that of computing the arc length. We have to find the derivative, square it, add 1, take the square root. But in these are constructed so this function f of x, the radius, multiplied in, helps us out tremendously. So just kind of see how that unfolds. Again, we're going to take the derivative to find the surface area of this function. And also note that we're integrating with respect to x in this formula because the function is revolved about the x-axis. So it's really only the shell and the washer method that you kind of have to think, all right, well, which axis am I revolving it around? Which variable do I integrate with respect to? With surface area, we are revolving a figure, but the variable of integration is always the axis you're revolving it around. So the derivative of square root of 4x plus 6. What's the derivative of the square root of 4x plus 6? So our function, again, we're going to view it as a power. This is 4x plus 6 to the power of 1/2, and this is a chain rule. So we have the derivative of the outer function, where the inner is left alone, times the derivative of the inner function. So let's go ahead and just combine the 1/2 and the 4. there's our derivative, 2 times the quantity to the negative 1/2. And then we're going to take the derivative and square it once again. So we have our 2 squared, and then we have the quantity to the negative 1/2 squared. So the derivative squared gives us 4 times 4x plus 6 to the negative 1. And we're going to add 1. So here's the thing, here's the trick with this. If I just add 1 like that, it's not helpful, because what I have to do is then take the square root of all of this stuff, right? Moreover, not only do I have to take the square root of it, but when I compute the surface area, I have to say it's 2 pi times the function times the arc length. So this is initially what we would be looking at if we didn't put any more work into this. But the only other thing you can try to do is, since they're both radicals, is to distribute this 4x plus 6 to both of those. But then you're still integrating 4 over 4 plus 1 over 4x plus 6, all under the radical. So it's like, do you want to integrate this as well? It's not that much better, is it? So with surface area in particular, the way to make it better is in this step when we add 1 to our function. So instead of adding 1 as 1, typically you want to add 1 as a function. Like as a function here, we would say this first term is just 4 over 4x plus 6, right? So when I add 1 to this, I want to add 1 in the way I add 1 by adding 1 like this. And in that way, the thing under the radical now is 4x plus 10 over 4x plus 6. So to see, again, why that's effective, we're just going to put that result here. And I guess it doesn't matter when you do this, it's just at some point, you got to keep in mind the structure of the whole formula you're trying to integrate, because now what happens? Right, this root on the outside cancels with the root on the bottom. So we just end up with the root of 4x plus 10. Because remember, this is actually just this. And this cancels with this. So you've got 2 pi. I guess we'll put our bounds in. So it simplifies to something a lot more manageable. And we went from 0 to 5. Those were the bounds that were given to us. So with surface area, for these problems that we have in this section, when you add one, you want to add one in the form of, you know, whatever function you have after you squared your derivative. Because that will always cancel out with the function f of x out front. Do y'all have any questions?
Since you're multiplying that radical by that radical, radicals want to go away because they're not the same function, right?
Right. Yeah. Yeah. It would have to be they would have to be the same argument underneath. Oh. Okay, so how do we evaluate this? Use substitution, right? You're gonna let u equal 4x plus 10. du is 4 dx. Or 1/4 du is dx. And there's our 1/4 du for our dx. We still had our 2 pi and the square root of u. Okay, our bounds on x were from 0, so if x is 0, u is 10. If x is 5, u is 30. So we can certainly integrate that. It's kind of the point of the algebra, I guess.
Is it cool to just put it back into x
Yeah.
afterwards?
Yeah, you can find the antiderivative, you know, u to the 3/2 times 2/3, and then say that's 2/3 times 4x plus 10 to the 3/2, and then use 0 to 5 if you want. Yep. So we get pi over 2 times 2/3 u to the 3/2 from 10 to 30. So we have pi over 3. We got 30 to the 3/2 minus 10 to the 3/2. So we'd either say write this as an exact value or round. Just got to be careful. So I think as an exact, we really can't. Some of these radicals aren't going to go away. So we'll just write it as pi over 3, 30 to the 3/2. Minus 10 to the 3/2. So that's about as exact as we can get. We can factor out a 10, but good enough. I didn't compute that decimal.
say 138.96. So, you know, square units because it's an area. Does anyone have any questions on that?
And on the test, you'll let us know to use exact, forms or decimal,
Yeah,
vice versa.
right. If on the test I don't specify, then do whatever. I don't have a preference. But a lot of times I will say exact. I don't know. It's with some calculators, it's hard to grade because a calculator would do all of that for you once you set it up. So a lot of times I'll just say exact because a lot of calculators don't give exact answers. And if you're able to get the exact answer, it kind of, you can kind of show me that you know what you're doing, I guess. If that makes sense.
Like if you get down to the pi over 2 times 2 over 3 with the bounds and everything, like showing that you did the integral and then you put it in your calculator, is that?
Yeah. So like stopping here at this stage, and then using your calculator, I think is fine. But some of it needs to be worked out. Like if you just, if you didn't cancel any of this stuff and you put like the mess we had in there in the beginning and you said, oh, just the integral of that times the square root of that is equal to, 138.96, clearly it's questionable how you got that because you probably just put it in your calculator. I don't know. Hopefully that's clear. It is, there is some ambiguity there, I get it, but we're in calculus, so we want to see calculus. I don't want to see calculator stuff. All right. Any other questions? So we've got 10 minutes, but I wanted y'all to work this one, and I don't think there's time to finish it in 10 minutes. So what I ask for next class is to at least do part of this number 14, and then when we come back on Tuesday, we'll finish this example. So just sometime before the next class meeting, have some of this done. Try to get the integral set up, try to finish it, whatever, just do something. You'll have a good weekend.